The art of algorithm development, crafting efficient solutions from concept to code in the ever-evolving landscape of technology. Algorithm development stands as the backbone of innovation. Whether you're optimizing search engines, enhancing machine learning models, or improving data processing speeds, algorithms are the silent heroes driving modern computing forward. This article delves deep into the world of algorithm development, exploring its intricacies, challenges, and best practices tailored specifically for developers and enthusiasts in the AlgoHey community. By understanding these principles, you can elevate your problem-solving skills and contribute meaningfully to technological advancements. Fundamental concepts in algorithm design. An algorithm is essentially a set of instructions designed to solve a particular problem or perform a specific task. It forms the core of any computational process, guiding how data is manipulated and processed within software applications. To design effective algorithms, it's crucial to understand fundamental concepts such as time complexity, space complexity, and correctness. These factors determine not only how efficiently an algorithm operates but also whether it will produce accurate results under various conditions. Time complexity measures the amount of time an algorithm takes relative to input size. Commonly expressed using Big O notation, which categorizes functions based on their growth rates. Space complexity refers to the total amount of memory used by an algorithm during execution. This includes both auxiliary storage requirements and the original input size. The role of data structures in algorithm efficiency. Data structures play a pivotal role in determining how effectively an algorithm performs tasks related to data manipulation. Choosing the right structure can significantly impact performance metrics like speed and resource usage. For instance, arrays provide fast access times but may be inefficient when inserting new elements at arbitrary positions. Conversely, linked lists allow efficient insertions/deletions yet require additional overhead due to pointer management. Selecting appropriate data structures. When developing algorithms, selecting appropriate data structures becomes critical for achieving optimal efficiency. Factors such as expected operations frequency, data volume, and required response times must guide this decision-making process. Consider scenarios where frequent searches might necessitate hash tables over binary trees. Similarly, situations requiring sequential traversal could benefit more from arrays than queues or stacks. Common algorithm paradigms and techniques. Understanding common paradigms helps developers approach problems systematically while leveraging established methodologies proven through years of research and application. Key paradigms include divide and conquer, dynamic programming, greedy approaches, backtracking, etc. Each paradigm offers distinct advantages depending upon the nature of the problem being solved. For example, divide and conquer strategies break down complex issues into smaller subproblems that can then be independently resolved before combining solutions. Designing algorithms through problem analysis. Before writing code, thorough analysis of the problem domain is essential. Identifying constraints, defining inputs/outputs clearly, and considering edge cases ensures robustness across diverse use scenarios. Problem decomposition techniques often reveal patterns useful for applying known solution frameworks. Recognizing similarities between current problems and previously encountered ones enables reuse of existing knowledge rather than starting afresh each time. Evaluating algorithm performance using benchmarks. Benchmarking provides objective measures against which different implementations can be compared objectively. Establishing baseline performances allows identification of bottlenecks early in development cycles. Tools like profilers help pinpoint areas consuming excessive resources without manual inspection alone. Regular benchmark updates ensure continued relevance amidst changing hardware capabilities and evolving standards. Optimizing algorithms for real-world applications. Real-world environments impose unique demands beyond theoretical considerations. Constraints such as limited bandwidth, variable latency, and unpredictable workloads challenge traditional optimization assumptions made during initial design phases. Adaptive algorithms capable of adjusting behavior dynamically based on runtime parameters offer resilience against environmental fluctuations. Incorporating caching mechanisms further enhances responsiveness by minimizing redundant computations. Challenges faced during algorithm implementation. Despite meticulous planning stages, implementation hurdles frequently arise due to unforeseen interactions among components or limitations inherent within chosen technologies. Debugging becomes particularly challenging when errors manifest only under specific configurations or load conditions. Cross-platform compatibility issues sometimes surface unexpectedly, especially when porting high-performance routines written originally for specialized architectures onto general-purpose systems lacking similar optimizations. Best practices for successful algorithm development projects. Establishing clear documentation protocols from inception aids long-term maintenance efforts significantly. Detailed comments embedded directly within source files enhance readability while facilitating quicker onboarding processes for future contributors. Prioritizing modularity promotes easier testing procedures via unit tests covering individual functionalities separately instead of relying solely upon end-to-end verification methods prone to cascading failures. Future trends shaping algorithm development landscape. Rapid advances in artificial intelligence and quantum computing promise transformative changes impacting algorithmic approaches fundamentally. As these fields mature, novel paradigms emerge offering unprecedented levels of abstraction coupled with enhanced analytical power. Integration of AI-driven tools assisting human designers through automated suggestions increases productivity substantially. Quantum-inspired algorithms already show potential improvements over classical counterparts regarding certain types of mathematical modeling tasks. Conclusion: algorithm development remains central to advancing digital technologies globally. Mastery of underlying principles combined with practical experience empowers practitioners to innovate continuously amid shifting industry landscapes. By embracing rigorous methodology grounded in sound theory alongside empirical validation techniques, professionals can confidently navigate complexities associated with creating next-generation computational solutions tailored precisely towards real-world needs.